So good afternoon, one and all. My name is Sanjeet Gariwal. I am from Department of Physics, Netaji Subhash University of Technology, Dwarka, Delhi. Today I am going to present my paper on the title CTAB Assisted Hydrothermal Synthesis of MO3 Nanoparticles, Multifaceted Characterization and Analysis. My paper ID number is 256. So let us discuss the objective. So in the objective, by using hydrothermal method, nanoparticles of MO3 were synthesized in the presence of CTAB, focusing on optimization, characterization, and performance evaluation to study the surface modification and investigate material enhancement as a potential contender in photodetector. In the coming slides, we will be discussing introduction, synthesis, result and discussion, conclusion part. Let us begin with a brief introduction of MO3. MO3 is an anhydrous compound which is a transition metal and exhibit various properties. It is composed of molybdenum and oxygen. It holds importance across multiple domains due to its unique properties. Some of them are it has a semiconducting nature, which means it allows control flow of electron, which is essential for photodetection mechanism. It also shows optoelectronic properties. That means it has capability to convert light energy into electrical signals. It also shows photoconductivity, that it ability to change conductivity on exposure to light with a wide band gap and tunable properties. The materials we have used in the process is ammonium molybdenate tetrahydrate, cetyl trimethyl ammonium bromide, and nitric acid. So let us have the synthesis part. So first of all, 0.6 gram of CTAP was dissolved in 20 ml ethanol and stirred for 20 minutes. Simultaneously, 3 gram of AMT was dissolved in 100 ml DI and magnetic stirring was done. Nitric acid was also added to maintain the pH of the solution. Thereafter, the sample was transferred to 100 ml Teflon autoclave and placed in hot air oven at 180 degrees Celsius for 20 hours. Thereafter, the sample was let down to cool down naturally, and centrifuge machine was used to remove the impurities with multiple times washing with DI and ethanol. Thereafter, the sample was placed in a vacuum at a 60 degrees Celsius temperature for 24 hours, and the sample was grind to get the fine powder. In the results and discussion part, we'll be having a look at FESAM, UV visible, and XRD patterns. So let us begin with the XRD pattern. So this is the XRD pattern of the sample, which matches the JCPT's file number this, and it comes out to be molybdenum oxide of monoclinic crystal structure. In the structural analysis, this is the 3D structure for the same. And as the structure came out to be monoclinic, using the formula, we calculated the lattice parameters, which came out to be as shown. Williamson Hall plot and size strain plot were also plotted, and using the values of slope and intercept for both, the crystallized size was calculated. The crystallite size, it was basically calculated using device sharer method, Williamson Hall plot, and size strain plot using the equations given. And the crystallized size came out to be 19 nanometer, 11 nanometer, and 7 nanometer respectively. In the optical analysis, the UV visible spectroscopy was performed in the range shown. The absorbance was recorded mainly in the UV region, especially between 200 to 300 nanometer. Thereafter, using the Pierre-Lambert's law, optical band gap of the sample was calculated using the equation, and it came out to be 3 electron volt. Also, the refractive index was calculated, which came out to be 1.91 using the equation given below. Here is the absorption spectra in the top plot. So here we can see that the absorptions is mainly in the UV region for the sample, and top plot provides us the value of the band gap. In the morphological analysis that shows in the presence of CTAP or MO3 showed formation of structures like nanorod with high surface area to volume ratio, and surface of sample showed irregularity and roughness also. EDX analysis showed that it was done in conjunction with SEM to determine the presence of different elements in the sample. The EDX pattern depicted the presence of molybdenum and oxygen with high intensity peaks. So in the conclusion, we have synthesized our MOO3 in the presence of CTAP by facile hydrothermal route. In the structural analysis, we calculated the lattice parameter, crystallized size, considered strain, and the phase of the sample came out to be monoclinic. In the optical analysis, our sample showed absorbance in the UV region mainly, with a band gap of 3 electron volt and refractive index 1.91. In the morphological analysis, basically structures like nanorods were seen. So therefore, with all these, the synthesized material is favorable for wideband gap photodetector applications. Thank you.
My topic is information of nano and micro scale hierarchical structures in MGO doped quantum dots doped LC media. And we have also highlighted the role of competitive forces in this paper. This was a PhD paper of Archana Kumari Singh. She been awarded PhD degree. So the first question is, what do we mean by hierarchical structures? So hierarchical means we first prepare quantum dots separately. Then there are quantum dots. We allow them to self-assemble in some presence of some media. Their aggregates are prepared. We can have different designs, nano wires and nano quantum dot wires, and then of course ring-like structures. There are other morphologies which may appear. It is an outcome of the self-assembly, and of course the outcome of the competitive forces in order to minimize the free energy of the hybrid system. So different steps are involved. I shall highlight those steps. Uh, First, we have studied the effect of ZNO MgO nanoparticles doping on liquid crystal media 4 trans 4 and hexacyclohexyl isothiocyanate benzoate 6CHBT. It is short form. It is called 6CHBT. I am audible.
Yes, sir, you are audible, but your slides are not changing.
Slides are not changing.
Yes, yes,
Highlight
now
is not visible.
highlights. Yes, yes. Yes,
That
sir,
is
now
okay.
change. Yes, yes.
Okay. So these are the key points we have prepared, and the ZNO MgO nanoparticles. Then mixed it in 6 CSBT liquid crystal. We have compared dielectric, optoelectronic, and calorimetric properties of MgO ZNO nanoparticle doped liquid crystal media. Prepared. Uh, uh, we have prepared the media and these nanoparticle dots in presence of toluene, and then we have gradually removed it so that we can transfer it homogeneously mix, and we have evaporated toluene. We have placed in glass cell and ITO coated glass cell, two different kind of surfaces. We mainly observe three different type of microstructures: grain-like structures from smaller MgO nanoparticles, then honeycomb-like mesostructures are found on glass surfaces. These MgO nanoparticles combine together to form honeycomb-like structures. And of course, in some cases, as in the case of ITO surface, flower-like clusters are formed. So all these things are done with the intention that we can tailor the optoelectronic properties by their natural self-assembly process. Designing these things at nano and micro scale would be very costly if we are using the idea of lithographic technique. So smaller nanoparticles allow anchoring of liquid crystal molecule, while larger nanoparticles separate out from the form bigger crystals. We have done characterizations and so on, FTR, Raman, ICRD, FESAM, EDX, etc. So the slide has changed. MgO nanoparticle, in flow chart, figure 2. Is it visible,
No,
sir?
sir. No, sir, no, sir.
Please wait. After highlights, synthesis of MgO nanoparticles appeared.
No, sir. No, sir. You click on the slide
Network.
number, sir, on the left bar.
Okay, okay, sir.
Then, yes, now
Okay,
the flowchart came, sir.
right. Okay, sir.
Yes, sir.
So this is how we have prepared. Magnesium acetate hydrate was taken. It was mixed in 150 milliliter of ethanol. We did continuous stirring using magnetic stirrer, and then aqueous solution. We obtained its aqueous solution in methanol. Uh, we have prepared aqueous solution of this oxalic acid to maintain pH. uh, we drop it and mix it together so that to maintain the pH to be 5. Stirring and heating clear, we do it, and when the pH is maintained goes around 5, we obtain clear solution. Still, we do stirring and get lastly we get white gel. White, then we filter it and wash it 4 5 times in deionized water. There is small particles of MgO formed. Different sizes may be there inside this in this method. There is a drawback. So what we do ultrafiltration using nylon filter of at the filtered particles at 200 degrees centigrade for 24 hours. In order to remove, we have water. We have annealed the particles for 550 degrees centigrade 6 hours. So this way we get the next. Next task is to synthesis of hybrid system. Figure number 3 is visible, sir.
Yes, sir. Yes, sir.
Okay. So next thing, once we prepare the MgO nanoparticle, then we have to mix it in liter. We take 6 CSBT liquid crystal. We take 5 milliliter of toluene, and then 0.5 mg of MgO nanoparticle. Continuous ultrasonification is done at 50 degrees centigrade for 3 hours. We get an isotropic solution of LC and quantum dot in presence of toluene, and then we use evaporation. For evaporation, we place it at 65 degree. Toluene is removed, and we are left with the homogeneous solution of MgO and liquid crystal, and then isotopic solution of liquid crystal. And next thing is that we use micro spacers are there of 60 micron thickness. Small films are there, so we just place between two glass slits, glass surfaces, and seal it from other three side, and with the help of capillary tube we just pour this small amount of liquid crystal and quantum dot inside the cell. So we do it for the MgO mainly. If we again we have also synthesized, our previous group members have synthesized ZNO nanoparticles. So we repeat the same process, simple process, and prepare a hybrid system of liquid crystal 6 CSBT with ZNO quantum dots. So next thing comes to result, which we have done FTIR to confirm whether the pure MgO and ZNO quantum dots are prepared. So FTIR
Please
spectra mainly
compile it in
confirms
2 to 3 minutes.
right,
The
sir.
time is very late.
Yes, yes, sir. So this is the FTR spectra, right, which confirms and purity also. So keeping in view of the time also, I just show some of the pictures which are important. See, this thing is in FTR spectra. What is the main task? We have pure LC, FTR spectra, MgO doped doped LC. So of course, if you see that the position of the peaks are not changing, you can clearly see that there are 3 cases: pure LC, MgO doped LC, and ZNO. There are no. So, and but the intensity, there are intensity variation, transmission intensity varies. So of course that is a result of this presence of quantum dots. So what we infer that there are no chemical shift, there is no chemical bonding between MgO quantum dot and liquid crystal. Similar way, there is no chemical bonding, we hope so. No, if the chemical bonding is done, then significant crystal bonding is done, then there will be a major shifting in these positions that doesn't appear. So of course we were interested in the physical interaction of the liquid crystal and these nanoparticles that we highlighted. We have published this in condensed matter physics, one Ukraine journal, and quite old, but they are very demanding. Right. So this figure figure number 6. This is XRD spectra. May I show it in a smaller? So this is XRD spectra, sir. Visible?
Yes, sir. Yes, sir.
So we confirm that it is a crystalline behavior, MgO and ZNO. We have compared with their JCPD scar and so on. Next thing, we do UV visible NIR spectroscopy analysis in order to obtain the band gap of these nanoparticles, MgO and ZNO nanoparticles. We obtain the and calculate the band. So one way is to obtain the edge wavelength, and another way is we use the chalk formulation, which is most commonly used for obtaining band gap. Both values are quite close. That is the thing. You see here we have the top plot and so on. So the band gap value of MgO was something around 4.95 electron. Is up 5.665. So next thing, what we do, what we infer here, you can see there is a variation of energy band gap of ZNO nanoparticles with size. So ZNO nanoparticles, when these particles are present in liquid crystal media over a glass surface or ITO coated glass, particles try to form aggregates. Some kind of unique structures or morphologies are formed, and we see there is a Bruce model in which they predict the energy band gap size. So there is a formulation on the basis of nanoscale principle. Shape, size are the important features which decide the band gap. So we can predict. You know the energy band gap in case of bulk material. You know the energy band gap of different size particles. Then you can predict in between what if the size is this, what will be the band gap. If the size is this, what will be the band gap. We confirm. And for different shapes, you have spherical, tetrahedral, hexahedral, and octahedral. Different kind of clusters can be formed. So what Bruce has suggested, sir, that was for a single particle. Means MgO means a completely formed MgO particle. It is a single unique particle, isolated particle. But we have extended the idea because in this case, smaller nanoparticles are forming a bigger aggregated particle. So that appears spherical in shape, not a single particle. The spherical particle which we are showing here with the size and band gap, that is the aggregate, spherical aggregate. It may be the tetrahedral. So we see that the spherical speculation, the spherical type of aggregate is confirmed. It is not easy to confirm that kind of aggregation with the help of any imaging tool. So we have used this predictive model for the first time. We have done it. So then you can, I should show you this optical microscopy images. So these are important. You can see what I have told you, that different kind of structures are formed. Here you can say network like, sir, it is visible? Figure number 10.
Yes, sir. Sir, please wind up. Sir, please wind up.
Bus 5 within 2 minutes. Structures are forming.
Thank you.
Here you see small nanoparticles are there, network form. Because they are connected and form, they have harmony with the liquid crystal. They can minimize energy because they are hosted well in the liquid crystal, and they can form this kind of structure. But you can see here in figure number C, their bigger clusters are formed. They are micron size spherical clusters are. These are not. These structures don't have any unique morphology and so on. So this is something. And this thing, what we have confirmed in case of this is MgO nanoparticle dopes is an ITO coated. When we are using ITO coated glass, you don't see any special structure. This is just cluster. Small aggregates are forming this kind of. So because the interaction with the ITO coated glass and MgO nanoparticle and the liquid crystal, when we the energy, compare the energy balance, there is no energy balance, and this kind of structure is obtained. But in case of MgO, this is again the ZNO case on ITO coated glass. So, and this is the IR spectra, emission, same images. So optical microscopy images further confirm the help of phase emission is centimeter microscope, we confirm that these kind of structures are formed because the in case of aggregates, these kind of cluster aggregates are formed. In the first, it is formed nanoparticles formed micron size is filtered out and those are formed hydrogen the liquid crystal goes hydrogen surface. So both things, Jedendo and you have different morphologies. It is clearly visible. I have shown you, and the whole idea is to the energy criteria, mineralization criteria. F is this is the EDEX image for the two cases, which confirms the elemental presence, and therefore there is no impurity and so on. So we are fully confirmed that no impurity is present and so on. So we have done the reverse demanded. Why not do you show some thermal DSC thermogram of these pure and doped cases we have shown, so that one may find some application. Again, the suggestion came from the reverse. So dielectric properties measurement we have also done. So this is the thing, and so these are the conclusions. One thing I would highlight that in case of band gap versus size variation, MGO and JNO have different behavior. In case of JNO, if the particle size is small, band gap is high, and when the particle size moves toward the bulk size, the band gap decreases. Opposite, but MGO nanoparticle case, we obtained the different opposite case. Why? Because it is suggested that MGO has some electromagnetic interaction, some kind of MGO that is not present, but in case of MGO that is there. So that we have also reported that thing, and therefore finally we conclude these conclusions are there. These are the references, sir, and thank you for giving me.
So good morning, everyone. So this is Dr. Shayan Bayan. I'll be talking on the development of triboelectric nanogenerators for cell power sensing application. I belong to Department of Physics, Rajiv Gandhi University, Arunachal Pradesh, where we are developing such triboelectric nanogenerators for sensing application. So first of all, we need to understand what are cell power devices. So the existing power sources, which are the common batteries, are heavy in weight, bulky in size, and also they are threatening to the environment. So if you think about the concept of nanorobot, so the implementation of nanorobot in human body is facing a challenge because of such kind of bulky power source, because the size of the nanorobot is very small and the power source which we are using right now are quite heavy to be incorporated within a human body. So we need alternative sources of power source, just like if we can harvest environmental energy which are around us, then we can have some cell power devices. Just we have the example of solar cell. Now we can also harvest mechanical energy which are around us. So using that kind of mechanical energy, one can convert it to a electrical energy. So the concept of triboelectric nanogenerator is based on the conversion of this random mechanical energy into electrical energy. What happens here? Here two materials are backed up by two electrodes, and they are connected by a wire. So there is a sufficient gap between two materials. Whenever a mechanical force is applied on a particular side, then the two materials will come in contact with each other, and there is a charge separation. And once they are separated, when the two layers are separated, then there is a formation of electrical potential. Because of this electrical potential, there will be a flow of current, and once they are completely released, they are in equilibrium position, all the charges are compensated, so there will be no flow of electron. And once you press it again, then there will be a reverse potential, and because of the reverse potential, there will be a backflow of electron. That's why you will have one upper peak and lower peak in the electrical output, whether it is voltage or it is current. So using the concept of triboelectric nanogenerator, we are developing human motion sensor, gesture sensor, temperature sensor, and sweat sensor, because these nanogenerators are largely dependent on the extent of contact, how much pressure you are applying on, and what are the environment, that means the temperature or any exposure to chemical species, etc. So we are at the northeast part of the country. It is Rajiv Gandhi University, and this is my lab, Nanoscale Energy Laboratory, and we have certain funding agencies, and we are having some experimental facilities just like chemical lab, then your electrical measurement system, dark room, basic electronics, etc. And we are fabricating this kind of triboelectric nano generators. So first of all, the application as human motion sensor. So this is the schematic of the device, and here you can see this is the uh, proof of concept prototype device which we have developed. This is the logo of our university, and this is the logo of our lab. And what are the components of we have used? We have used gold decorated graphitic carbon nitride, zinc oxide nanocomposite, common cellulose paper, Teflon, aluminum foil, and PP tape. So these are the ACM, FSM, sorry, field emission scanning electron microscope images of the nanocomposite. So here you can see these are nano rods which are wrapped by a gold decorated graphitic carbon nitride. So this has been used as the active material in the device. So once we are attaching this kind of device on a human body, so you can see for the three sensors are placed on the three different parts of the body, and one can find that with the movement of the finger or the movement of the elbow or with the movement of the neck, one can generate different output voltages. And here is a demo of the experiment. So one device has been attached on the finger, and you can see with the operation of the finger, the output are displayed on the DSO. And now one can say that the extent of this voltage generated from this kind of device depends on the extent of contact, and also it is dependent on the frequency of operation. So it is working as a self-powered motion sensor. Next, you can see we can also send the signal of such kind of sensor in from one place to another place, just like the transmission of the sensor data from one place to another place, and that will be quite easy for remote access of the data. So you can see here in the mobile, we can transmit the data which is being generated on the device here, and the output can be seen here in the laptop. Now similar kind of triboelectric nano generator based sensor has been used for developing gesture sensor for differently abled people. So here you can see the band like shape of the sensor, and this is quite flexible, and whenever they are attached on the five sensors have been attached on the 5 different fingers, and the output has been measured using simple Arduino based circuit. And one can see with the representation of different numerics like 1 to 5 or the alphabets A to F in sign language, one can have different output signals. And we have used machine learning techniques, the random forest algorithm, to predict the sign in the expressed sign language or the numeric representation, and we have found a accuracy around 96% while this recognizing and predicting this output of the sensors. Similarly, we have also developed wearable temperature sensor. So here you can see this is the schematic diagram of the sensor, and here we have used the active material as graphitic carbon nitride zinc oxide nanowalls. So this is the FSM image of the active material, and here you can see one batch of such kind of sensor, and this is the band of this kind of sensor. So whenever this sensor has been attached on a finger, and we have checked with the hot and cold beakers, so one can see that while touching the cold water in a beaker, I can have a voltage around 5 volt, whereas whenever I'm touching this at a higher temperature, the voltage increases. So this shows that such kind of device can also work as a temperature sensor. Now this kind of proof of concept prototype has been attached on a shoe of a user, and to verify whether there is a actual rise in temperature or not, there is a thermocouple. We have also attached a thermocouple, and you can see the temperature can be displayed on the multimeter. So with the movement of the feet by the user with time, one can see that there is a gradual rise in temperature. Along with the gradual rise in temperature, there is a rise in output voltage. So one can see that the change in there is a subsequent change in voltage with the change in temperature. So this kind of temperature sensor can be used in regular activities. Similarly, we have also used such kind of triboelectric nanogenerator based sensor for sweat sensing application. So here this is the proof of concept prototype. Here this active part has been made on textile platform. So textile, the common cellulose, common cotton cloth we have used. So this is the FSM image of the cotton cloth, and over the cotton fibers we have developed zinc oxide nanorods, and we have checked the application of the sweat sensing of the by the sensor. We used saline water. So you can see with the different concentration of saline water, the voltage increases, and we have found a sensitivity around 0.02 volt per microliter with a detection limit of 4.8 microliter. Now, once this kind of sensor has been attached on the forehead of a person, and one can see that during warm up, this is the output voltage. The person, so you can see the video here. So the person is continuously doing some physical activity, and you can see that this output voltage is rising. So basically this initial part is originated from the warm up of the person, and this rise in voltage corresponds to the secretion of the sweat in the user. So in the conclusion, what we can say, we have fabricated flexible and wearable self-powered sensors, and we have harvested energy from human motion, and we have also shown the capability of remote location sensing, and this can predict different health status of a user, and many more are yet to explore. So these are different sensors which we have developed in our laboratory. So this work we have published in several journals, just like Sensor Actuators, say Nanotechnology, Nanoenergy, which is a high impact, around 17 impact factor journal. So this I would like to thank you all. So if there is any query.
My name is Dr. Sayantan Guha. I am currently appointed as an assistant professor at the Center for Data Science, Shiksha Anusandhan, deemed to be university, and I'm grateful to be invited to give a talk at the second international conference on recent trends in material sciences and devices 2023. So this is the title of my talk: Natures of reflected waves generated due to incident QSV waves at the stress-free surface of a micromechanically modeled PFRC half space. PFRC is short for piezoelectric fiber reinforced composite. Let's move ahead. So these are the contents of my presentation, and I'll cover each and every one of them separately. So firstly, let us start with the aims and objectives. So what are the objectives of this talk? So there are actually two parts. The first part deals with piezoelectric fiber reinforced composite modeling by analytical techniques, and the second part deals with wave reflection phenomena in it. Now, what are piezoelectric fiber reinforced composites? To understand that, first we need to know what piezoelectric materials are. Well, they are a special type of material that can convert electrical energy to mechanical energy and vice versa. And due to this energy conversion property, they have been used in many branches of science and engineering for many years. Here are some examples. They are used in sensors, actuators, transducers, ultrasound testing, and so on. But years of using them have brought out some of their negative attributes. For example, they are mechanically brittle and stiff. They offer low electrical outputs and so on. To overcome such hindrances, what we do is we combine these piezoelectric materials with other types of materials, and thus we generate composites to overcome the drawbacks. This is the first part. The second part deals with wave reflection phenomena, which is used again in many branches of science and engineering. For example, seismic exploration, geophysics, earthquake engineering, and so on. So actually, when waves propagate through a medium, they carry a significant information about it. And in order to understand about the inner constituents of the medium, understanding the wave reflection phenomena is very essential. That being said, let us begin. So this is the actual geometry of the problem. Here we have the x-axis, below we have the z-axis. Due to an incident QP or QSV wave through the PFRC half space, making an angle theta with the z-axis, we have a couple of reflected waves. How did we construct this structure? we have performed an analytical micromechanical model. These long strips are the piezoelectric fibers for which we have used PZT5A, and the gray area outside is the surrounding epoxy material which acts as the matrix material. So we start with the equations of normal stress strain relation equations. The stress equation, electric displacement equation of the fibers given by 1, and the piezoelectrically inactive matrix equations are given by 2. The terms are given over here. Now, as per the geometry of the problem, the piezoelectric fibers are oriented along the x direction. So the strains acting along the x direction are same. The other strains are given by rule of mixtures as equation 3. Here, omega f denotes the fiber volume fraction, omega m denotes the matrix volume fraction, and they're related by omega f plus omega m equal to 1. Similarly, the stresses are given by 4, electric displacements are given by 5, and density is given by 6. On combining all of these equations and using the techniques of strength of materials, we have finally derived the expressions of the electromechanical constants of the PFRC. The expressions are later given on in the appendix. So here we are going to see whether we actually get any advantage of the PFRC over monolithic materials or not. As I mentioned earlier, for piezoelectric fibers we have chosen PZT5A, and for epoxy and for matrix material we have chosen epoxy. So let us observe figure A. What is happening when omega f lies between 0 and 1? As omega f keeps increasing and gradually takes value 0.9, the value of E31 bar is 1.26. What is E31 bar? It is E31 of the PFRC divided by E31 of the piezoelectric fiber. So when omega f is 0.9, E31 bar equal to 1.26 implies E31 of the PFRC is 1.26 times greater than E31 of PZT5A, which ensures that our PFRC, when fiber volume fraction takes value 0.9, has a greater magnitude of piezoelectric constant compared to PZT5A. This greater magnitude of piezoelectric constant is very useful in sensor and actuator applications. From figure B, we can see when omega f takes value 0.9, the dielectric permittivity epsilon 11 is 1.45 times that of PZT5A, and epsilon 33 of the PFRC is 1.51 times that of PZT5A. These greater magnitudes of dielectric permittivities are useful in capacitor applications. In figure C, we see that the magnitudes of density and stiffness constants of the PFRC are lesser compared to PZT5A. This ensures that the PFRC is low density and mechanically flexible, which is very useful in electroelastic transducer applications. Lastly, here we see why we have chosen epoxy as the matrix material. So calculations reveal that as the magnitudes of the stiffness constants of the matrix material keeps increasing, E31 bar and E33 bar keep decreasing. But we want higher values of piezoelectric constants, not lower ones, and higher values are obtained when low magnitudes of stiffness constants of matrix material are chosen. That is why we have chosen epoxy material as the matrix, because we can see later on from the data that the magnitudes of stiffness constants of the matrix are much lesser compared to PZT5A. So this part concludes the advantages of PFRC. Now let us move on to the second part of the problem, analysis of wave reflection phenomena. Here is the geometry. Once again, due to an incident QP or QSV waves, 3 reflected waves are generated in the half space: a reflected QP wave, a reflected QSV wave, and a reflected electroacoustic wave, which is an evanescent surface wave propagating along the x-axis. So these are the standard equations which we use to solve the problem. We have the stress-strain relation, strain displacement relation, Gauss law, and so on. Now, on applying these equations as per the geometry of the problem, we obtain equations 12, 13, and 14, which are highly coupled PDEs which we need to solve. So since we are dealing with 3 reflected waves, the reflected quasi-longitudinal wave, the reflected quasi-transverse wave, and a reflected EA wave, there are 3 unknown waves, and in order to understand the natures of the 3 unknown waves, we are going to require 3 boundary conditions. 2 of them are mechanical type, and the third one is electric type. To solve the equations, we assume a solution form given by equation 18, adhering to the generalized Snell's law. On applying this solution form in our 3 equations, we obtain a family, equation 19. From this family, we obtain the velocity expressions of the QP and QSV wave, as well as the propagation directions of all reflected waves, which can be seen from these figures. Observe figure A, for example. Here we have considered an incident QP wave first. So as the angle of incidence keeps increasing, so does the angle of reflected QP wave. Okay, that means angle of incidence is equal to angle of reflection. Now the QSV wave is slower than QP wave, and being slower, it propagates closer to the z-axis, which means its angle is lesser than angle of QP wave, as can be seen over here. The magnitude of angle of reflection of QSV wave is much lesser than QP wave. And the EA wave, being an evanescent surface wave, propagates constantly along the x-axis, which can be seen over here also. The EA wave, for all values of angle of incidence, propagates along a straight line, that is taking a constant value of 90 degrees. What happens for incident QSV wave? As the angle of incident QSV wave keeps increasing, the angle of reflected QSV wave also keeps increasing, which once again shows angle of incidence is equal to angle of reflection. Now, since QP wave is the fastest wave, as the angle of QSV wave keeps increasing, the QP wave angle also keeps increasing drastically until and unless it reaches theta equal to 29 degree, because at and beyond theta equal to 29 degree, it just passes along the surface as an evanescent surface wave. And once again, the EA wave propagates along the x-axis. So once all of these are derived, we finally have the expressions of the displacements, electric potential, the stresses and electric displacement of the medium. And on applying the boundary conditions, we obtain the final family of equations 22. Using Cramer's law, we finally obtain the amplitude ratio expressions of the system. So amplitude ratios are not enough to verify whether the entire energy of the system is conserved or not, for which we have derived the energy ratios. And as per the law of conservation of energy, we must have energy carried by the incident wave should be equal to sum of energies of all reflected waves, which I have shown graphically to hold. So these are the data that I've used. These are the data for PCT5A. These are the data for epoxy. For example, you can see C11 of PCT5A is 139 into 10 power 9, but C11 of epoxy is 3.86 into 10 power 9. The magnitude of C11 is much lesser than magnitude of PCT5A C11. That is why we chose epoxy as the matrix material. Let us go through the graphs of the problem. Here we have dealt with the energy ratios of reflected waves considering an incident QP wave. Observe a special case when theta equal to 0 degree, that is the incident QP wave strikes this slab normally. So it should go inside, it should hit this point, and it should come back as a reflected QP wave carrying maximum amount of energy, which can be seen over here. When theta equal to 0 degree, the magnitude of energy ratio of reflected QP wave is 1. That is the maximum magnitude. Now when theta keeps increasing, the energy carried by the incident QP wave is distributed among the QP and QSV waves. So the QP wave keeps losing energy after theta equal to 0 degree. But since the law of conservation of energy is a universal law, energy should remain conserved. So what is happening to this lost energy? The energy that is lost by the QP wave is now being gained by the QSV wave. Okay. Now as theta keeps increasing further, we observe that whatever is happening for QP wave, the reverse is happening for QSV wave. And ultimately, when theta is equal to 90 degree, that is the incident QP wave passes along the surface, it just moves on as a reflected QP wave carrying maximum amount of energy. So at theta equal to 90 degree, the energy ratio of the reflected QP wave takes maximum magnitude 1 and that of the QSV wave is 0. So sum of these two is mainly 1. Now what is happening for the reflected EA wave? Since the reflected EA wave is an evanescent surface wave, it does not carry a significant amount of energy because this wave is not moving in and out of this medium, it is just moving along a straight line. So we can see for all values of angle of incidence, the order of magnitude of energy ratio of reflected EA wave is of order minus 15. So entire energy ratio is something into 10 power minus 15, which is almost negligible. Now, at this point, the waves are also interacting with each other, and the energy of interaction has order of magnitude 10 power minus 14, which is also quite negligible. Now, finally, what I've done is, for all values of angle of incidence, I have found out the sum of energy ratio of reflected QP wave, reflected QSV wave, reflected EA wave, and interaction energy ratio up to 7 decimal places for accuracy, and I have found out that the net energy is equal to 1. So actually the energy is remaining conserved in this study considering an incident QP wave. Let us come to the final set of graphs for the following problem. Here we finally consider an incident QSV wave. Last time we had considered an incident QP wave. Now we consider an incident QSV wave. And over here once again I have provided the geometry of the angles of propagation of all reflected waves. This geometry is going to be important in this figure. Let us observe what's happening. So since we are dealing with an incident QSV wave, it can be seen that when theta equal to 0 degree, once again, as the QSV wave moves along the z-axis, it hits this point and it should come back as a reflected QSV wave carrying maximum amount of energy, which can be seen from figure B. In figure B, we have plotted the energy ratio of reflected QSV wave. It can be seen when theta equal to 0 degree, the magnitude of energy ratio is 1, which is maximum. Now, as theta keeps increasing, the incident QP wave energy is being distributed among the reflected QP and reflected QSV wave. So initially, the reflected QSV wave carried maximum amount of energy. Now, with increasing values of theta, the QSV wave keeps losing some energy. But as per the universal law, energy should remain conserved. So what's happening? The energy that is being lost by the QSV wave is being gained by the QP wave, ensuring that the law of conservation of energy holds. Now we see that as theta increases and takes value 29 degree, the QP wave, being an evanescent surface wave, loses all energy. So at theta equal to 29 and beyond, the energy ratio of the yes, sir, this is the final figure. The energy of reflected QP wave is 0, and the energy of QSE wave is 1. Similarly, the EA wave energy has magnitude -15, negligible. Interaction energy is also negligible, and the sum of all energy ratios is 1, thus ensuring that the law of conservation of energy is true, and this concludes our problem. These are the concluding points which I have already covered. So I'm grateful to SOA University for providing me the opportunity, and also grateful to SKITM for inviting me. These are the appendices. These are some of the references that I have used. Thank you everyone for your time.